Let's walk through the process we can use to find the determinant of any square n by n matrix. We're going to find the determinant using cofactor expansion. If we have a square n by n matrix A, we can find the determinant by selecting the ith row or jth column and computing the following. In these summations, the Aij entries are the values found in our given matrix A, and the Cij values are the cofactors associated with the selected entries from our matrix A. So if we have a general 3x3 matrix A, we could calculate the determinant using any row or column. If we find the determinant of A using row 1, and following the summation, we get that the determinant of A is equal to A11 times C11 plus A12 times C12 plus A13 times C13. Effectively, we sum up the products of each term in our row with their associated cofactors. We could also calculate the determinant of A using row 2 and taking each element from row 2, multiplying them by their cofactors, and adding them all together. This is the general guide for any row. Similarly, we could get the general guide for finding the determinant by expanding on any column. Just take the entries of your column, multiply them by their cofactors, and sum them up. Let's use cofactor expansion to find the determinant of the following 3x3 square matrix A. Let's find the determinant by expanding across the first row. The first row is 1, 7, 5 here. Now, cofactor expansion for determinants tells us to take the first value, which is 1 in our row, and multiply it by its cofactor, which we denote by C11. We add the second value in our row, the 7, multiply it by its cofactor, C12. We add the third value in our row, the 5, and multiply it by its cofactor, C13. So the determinant of A is equal to 1 times C11 plus 7 times C12 plus 5 times C13. Well, what are the values of these cofactors? Remember, the cofactor of entry Aij is -1 raised to the I plus j power, multiplied by the minor of entry Aij, which we denote with capital Mij. That means we can replace C11 with -1 raised to the 1 plus 1 power times capital M11. Remember, the minor of entry Aij is the determinant of the matrix that remains after eliminating the ith row and jth column. Capital M11 is equal to the determinant of what remains when we drop the first row and the first column. The first index of capital M is our row number that we're dropping, and the second number in our index is the column that we're dropping to find our minor. M11 is equal to the determinant of 3892, the determinant of what remains after we drop our row and column. C11 is equal to -1 raised to the 1 plus 1 power times the determinant of 3892. We've replaced our cofactor C11 with its value. Now we want to replace C12, the cofactor that's multiplied by 7. C12 is equal to -1 raised to the 1 plus 2 power times the determinant of what remains when we cross out the first row and the second column. So we multiply by the determinant of 4862. We can replace C13 with -1 raised to the 1 plus 3 power times the determinant of what remains after we cross out our first row and third column, which is the determinant of 4369. We just need to now simplify these values we've subbed in for our cofactors to get our determinant. Let's start by handling these -1 raised to the I plus j powers next. We have -1 raised to the second power, -1 raised to the third power, and -1 raised to the fourth power. Any even power can be replaced by +1, and any odd power can be replaced by -1. Since the powers of these -1 terms is the sum of the row and column numbers, we can use this sign matrix here to remind us what -1 raised to the I plus j power can be replaced with based on the sign in the corresponding position to the value that we're picking from our matrix A. The sign in the upper left corner is always a positive symbol, and it alternates as you move across the matrix, regardless of the dimension of your square matrix. Since we're expanding across the first row of matrix A, we use the first row of our sign matrix to tell us the +1 or -1 values that exist within the associated cofactors of each entry. C11 has a +1, C12 has a -1, and C13 has a +1, because of the pattern of the first row in our sign matrix. What have we done so far? Well, we took the determinant of a 3x3 matrix and rewrote it as the sum of smaller 2x2 determinants. This sets up the recursive nature of cofactor expansion. You continue expanding until you have expanded to a sum of only 2 by 2 determinants. Why can we stop when we rewrite everything as a sum of 2 by 2 determinants? Well, that is because we can calculate the 2 by 2 determinants using this guide here, where we take the difference between the product of these two diagonals. We can replace this determinant with 3 times 2 minus 8 times 9, which is equal to negative 66. The next determinant becomes 4 times 2 minus 8 times 6, which is equal to negative 40. And the last one is 4 times 9 minus 3 times 6, which is equal to 18. At this point, we have all the elements we need to find the determinant. The determinant of A is equal to the first row entry 1 times positive 1, the value we got from the sign chart, times negative 66. And this was the first row entry times its corresponding cofactor. We add the entry in the second position, the 7, times the sign from the sign chart, which is negative 1, times negative 40. This is the second entry of our row times its corresponding cofactor. We add the third entry of our row, 5, times positive 1, times 18. This is the third entry of our row times its corresponding cofactor. This product equals negative 66, this product equals positive 280, and this product equals positive 90. Adding those together, we get 304. The determinant of A is equal to 304. We got that value by doing cofactor expansion across the first row of our matrix A. Quickly, let's validate this value by also expanding across the first column of matrix A. The first entry of column 1 is 1, and we multiply it by its corresponding cofactor. Its cofactor is equal to positive 1, this position in the sign chart, times its minor, which is equal to negative 66. 1 times negative 66 is negative 66. We add the second entry of column 1, which is 4, and multiply by its corresponding cofactor. Its cofactor we calculate using the sign from the sign chart is negative 1, and its minor is equal to negative 31. This product is equal to positive 124. The third entry of column 1 is 6, and we multiply it by its corresponding cofactor. The cofactor which equals positive 1 times 41. This product equals 246. Negative 66 plus 124 plus 246 is equal to 304. This is the same result we got when we expanded across the first row. Turns out, regardless of the row or column you expand across, you will get the same value for your determinant. Mainly, it just comes down to getting the values from the row or the column you select, their respective signs from the sign chart, and multiplying by their minors. For every single row and column option in our matrix A, we get 304 every single time. Knowing that we can select any row or column to do cofactor expansion, let's look at a 4x4 matrix and talk about how we select the row or column to make the calculation of the determinant as easy as possible. Consider this 4x4 matrix A. What row or column will make calculating the determinant through cofactor expansion easy to calculate? An easy way to pick is to select the row or column that contains the most zeros. Which row or column of our matrix has the most zeros? Well, column 3 has the most zeros, so let's expand down column 3. Using cofactor expansion, we get the determinant of A is equal to the value in the first position of our column 0 times its respective cofactor C13 plus the value in the second position of our column times its respective cofactor C23 plus the value in the third position of our column times its respective cofactor C33 plus the value in the fourth position of our column times its respective cofactor C43. What do you notice about 3 of these terms? 3 of them have 0 times a cofactor. So regardless of what the cofactor is equal to, the 0 is going to dominate it and make it 0. So really, the determinant of A using column 3 is going to be equal to 1 times C33. And that is equal to 1 times positive 1, the sign that's in the same position of our sign chart, times the minor of our entry. The minor of our entry here ends up being a determinant of a 3x3 matrix. This cofactor expansion allowed us to reduce the dimension of our determinant. We are now working with determinants of 3x3 matrices. Since this is my only 3x3 determinant I'm working with at this step, we now look in here and do the same thought process. Which row or column makes cofactor expansion easy to calculate? Well, column 3 of this determinant is easy to calculate because it has 2 zeros. Using cofactor expansion along the third column of this determinant, we get 0 times C13 plus 0 times C23 plus 1 times C33. 0 times C13 is 0. 0 times C23 is 0. So this determinant is equal to 1 times C33. What is C33? Well, it's the sign we get from the sign chart, so it gives us positive 1 times the minor we get when we eliminate the third row and third column of our 3x3 matrix. We're left with the 2x2 determinant 1, 2, 3, 5. This is equal to 5 minus 6, which is equal to negative 1. So we're left with positive 1 times positive 1 times negative 1, which is equal to negative 1. The determinant of this 4x4 matrix is equal to negative 1. By choosing the column that had the most zeros, we are able to kind of reduce the amount of calculations we have to do whenever we're doing cofactor expansion. So for some simple reminders, you can expand across any row or column. It's good practice to pick the row or column that has the most zeros. Each term of these cofactor expansions follows the same pattern. It's the entry of your matrix times the sign from the sign chart times the minor of the entry, which is just the entry selected times its corresponding cofactor. Check out this playlist for more videos related to linear algebra. If you found this video helpful, consider subscribing, liking, or leaving a comment to support my channel. I'm Joe, and thanks for spending some time with me.